costly and time-consuming real-world data collection through deploying drones for training machine learning models has led to utilizing synthetic data as an alternative for training the models in drone applications. Current aerial synthetic data generation methods are based on limited training simulation scenes that can cause the model to overfit and as a result generalize poorly to unseen environments. Accordingly, our goal in this work is to contribute to widespread generalization by introducing a scalable approach for aerial synthetic data augmentation to increase end data diversity. Current synthetic aerial data generation workflows rely on a procedural approach for configuring simulation scenes and generating data. The procedural model follows a manual configuration where the expert user needs to run the simulator with the desired scene, manually sample locations for assets and drone trajectory, and tune parameters that govern environment and drone agent. The simulation environment is rendered based on the specified configuration by data collection engine, and generated poses are sent to a virtual camera drone in the environment to record all required synthetic data. But the data generated through this model lacks diversity, and dependency on manual configuration creates challenges for larger-scale diverse data generation. Additionally, data augmentation can only be performed after data is generated, thus limiting diversity that can be applied to the data through larger-scale scene augmentations before the data is collected through the virtual camera drone. Augmenting the data through domain randomization, namely increasing the diversity of simulation environments to train a model over all the varieties, has been proved to be essential for widespread generalization. To address these gaps, we present ASDA, a new procedural generative aerial synthetic data augmentation framework. ASDA extends a central data collection engine by adding two pre- and post-processing scriptable pipelines that automatically perform scene and data augmentations. The pre-processing pipeline has built-in randomization operations that can be combined and applied automatically to different scene specifications that seed its generative scene augmentation process. The pipeline is implemented such that it can run a batch of operations attached to it to generate unbound number of scene variations based on operation specifications before feeding them to data collection engine. The post-processing pipeline has built-in augmentation operations that are applied over collected data to further augment the training datasets. Additionally, ASDA increases synthetic data generation efficiency by connecting scene and data augmentation pipelines to data collection engine and enabling flexible control through a unified prompt-based interface. To implement ASDA, we chose AirSim as our central data collection engine. AirSim provides a configurable high-fidelity simulation platform for synthetic data collection. We demonstrate ASDA's workflow for data augmentation by going through our experiment of generating data for a landing pad detection task over the Seattle simulation scene. The Seattle environment used for this experiment is one of the 3D city maps, which is supported by AirSim, and we use it to seed the generative scene augmentation process in ASDA's pre-processing pipeline. ASDA's generative scene augmentation is enabled through a layered domain randomization approach incorporated into its pre-processing pipeline, in which first the asset generation operations generate new variations of specified asset objects by randomizing their rotation, scale, and material to increase diversity in asset appearance. Generated asset variations then seed the distribution operations. To create an adaptive method for asset distribution over simulation environments for increasing diversity in asset placement, ASDA embeds 3D scene graph information to the distribution operations in the pre-processing pipeline. ASDA benefits from scene graph to extract the spatial and logical relationship of a graphical scene from the hierarchical representation of environment objects, and to use its traversability for querying the graph to find particular objects of the scene. Querying the scene graph per asset type results in extracting a subgraph that we call distribution space, which includes all the nodes representing the container objects over which the asset can be distributed over. To further reduce the subgraph to the boundary boxes that directly inform location sampling for responding landing pad assets, the distribution operation maps the subgraph to a distribution layer. This layer only includes boundary boxes that are polygons of the building's rooftops, as well as the relevant attributes such as the height of the buildings and their type. The asset variation generation and distribution over valid locations results in augmented scenes with diverse asset placement and appearance for data collection. Additionally, we implemented operations for obstacle generation in ASDA pre-processing pipeline that are applied in next layers of our domain randomization approach. These operations create diversity in asset and camera obscuration to further increase scene augmentation for end data diversity. To replicate camera obscuration, here we show how obstacle objects, which in this case are other drone objects generated in field of view of the main drone camera, can augment the scenes for data collection. Other operations in ASDA's pre-processing pipeline support domain randomization by randomly changing the global lighting and weather in simulation scenes to further increase diversity. The result of applying the additional scene augmentation operations for domain randomization increases diversity of generated data. Accordingly, the generated dataset using the original procedural model is transformed from this dataset to a vast augmented dataset. Additionally, after the data is collected over the augmented scenes, the post-processing pipeline further augments the dataset by applying image augmentation operations such as random flipping and visual effects. ASDA increases the variance in end data by 75% and makes data generation process 50% more efficient with its workflow. Additionally, ASDA's unified prompt-based interface and architecture contributes to a new approach for iterative data collection optimization. We can take the operations specified through the interface as a data generation strategy, and in each iteration generate data with a sample strategy to collect performance statistics. To meet the performance target, we model performance as a function of data size as well as the content gap to determine whether we need to change the setting and complexity or merely increase the data size for the next iteration. Based on performance statistics feedback over collected data, we update the magnitudes of operations to increase data size, or we update the sub-policies into a strategy to change rendering setting in collected data. ASDA's prompt-based interface for the pipelines can be integrated with large language models such as ChatGPT to support natural language for more fluid data generation experience. Accordingly, by linking the library of ASDA's pipeline prompts to ChatGPT, users can indicate their data generation goal for a training task, and ChatGPT can parse user intent and convert it to pipeline action prompts to write the data generation strategy. By using our proposed pipeline for data collection optimization in the loop as a feedback, we can improve the data generation strategy generated by the large language model and revise policies to apply targeted augmentations for improved generalization. We intend to implement this strategy in our future work to improve ASDA.